Today we are going to discuss a famous experiment of Michael Faraday, the Coil-Magnet experiment. Yes, it is looking apparently very simple, but here are the two cases. First one is I have a coil and magnet. Okay, there are two cases. There is coil and magnet. If I make the coil stationary and move the magnet, this is a case, and when I make the magnet stationary and move the coil just like this, it is another case. Yes, it is looking very simple that two cases are same, but these two cases are totally different. Sir Albert Einstein noticed these two cases and formulated the special theory of relativity. So look what is the two cases. The coil-magnet experiment. First case, I am taking that I have a coil and there is a galvanometer, okay, and I have a magnet. If I move the coil and make the magnet stationary, then what happened? Look, I make the movement of the conductor. When I move the conductor, there are many charges in the conductor and the charges also move, and the magnet creates a magnetic field. Okay, you know that a magnet creates a magnetic field. So when I move any charge in a magnetic field, there is a force acting on the charge, and the governing equation is that force V cross B. Okay, if the velocity is V of the conductor. Okay, so here the force acting on the conductor or acting in the charges on the conductor due to magnetic field of the magnet. Okay, if we consider the another case, so here is loop again, here is galvanometer, okay, and here is magnet. Now I make the coil stationary and move the magnet. Okay, so what's happens here? Here, when we make the coil stationary, that means the charges on the conductor is stationary, means at rest, they are at rest, but the magnet moves. Now tell me one thing, if charge is at rest, is there any force due to magnetic field? Because force due to magnetic field depends upon the velocity of the conductor or velocity of the charge, but there is no velocity of the charge or the conductor. So how the current flows? Here also a current produced, induced current, here also the same current produced. In this case the current produced, let I. So here similar kind of current, not exactly but I. Okay, if we all things are similar, then current will be also similar. Okay, so what is the difference here? Here the conductor or the charges on the conductor is at rest, so there will be no force due to magnetic field. So how the charges on the conductor moves? Here for the moving magnet or moving magnetic field, a induced electric field is generated. Here a induced electric field is generated because I am again telling you that a stationary charge or a stationary conductor, magnetic force will not act because is at rest, V equal to 0. Okay, so here what is happens, here we move the magnet, means the changing magnetic field creates an induced electric field. That means here the governing equation will be like this. So here is this and here is this. Is this equal? Sir Albert Einstein first noticed this difference, and he assumed that there is some laws of nature is there behind it that yet to be discovered, and from this phenomena Einstein formulated the special theory of relativity. The special theory of relativity, on that research paper he published, the research paper is not named as special theory of relativity, it was named as the electrodynamics of moving bodies. Electrodynamics. It is the research paper on which Sir Albert Einstein published his special theory of relativity. In the first 2 paragraphs of that research paper is that experiment, this basic experiment. Okay, so we are looking at the simple experiment, but it is not as simple as that. There is 2 different cases. Thank you.